All right, so today our dream speaker is Meeko Oishi, an associate professor from UNM, the University of New Mexico. Meeko received her PhD and MS from Stanford, and she was advised by Claire. Meeko has a wide range of research interests, including human-in-the-loop systems, hybrid systems, and treatment of diseases. She has received many awards in both research and teaching, including the NSF Career Award and the UNM Regents Lecturer Award. Before joining UNM, Meeko was at the University of British Columbia, and I was very lucky to have her as my supervisor. I'm really excited to hear her talk today, so please welcome Meeko.
Thanks, Mo. Okay, so today I'm going to be talking about some of the work going on in my lab at UNM. I'm going to be focusing in particular on collaborative control of human-in-the-loop systems, our work not only in control, but also in interface design. And the work that I'm presenting is joint work with my students, current and former students. So my lab focuses on two broad areas right now. So one is formal methods for cyber-physical systems that have potentially a human in the loop. And the other one is feedback mechanisms in the brain. And I'm going to be talking about both of these projects, or both of these areas today. We've been interested in looking at problems in user interface design. So how do we find methods that allow us to design formally for user interfaces for certain classes of systems that are going to satisfy certain good design requirements a priori. We've also been looking at problems in constrained collaborative control that I'll be talking about today in collaboration with some folks in motion planning and computer science, and also space vehicles and control. This is work with the Air Force Research Lab, where we're looking at space vehicle rendezvous and docking. For the biomedical work, we've been looking at a variety of problems which have in common that they are about feedback mechanisms in the brain, but they are quite diverse. So in Parkinson's disease, I'll talk a little bit about this because it relates to characterization of the human. We've been looking at problems in motor control, where we're trying to characterize some of the behaviors that we see in Parkinson's subjects as a way to try to elucidate underlying faulty feedback mechanisms in the brain. I also have some work going on with an NSF ERC that UNM is a part of, and smart lighting for circadian rhythms, amongst other things. We're looking right now, and we have a picture. We just built this new facility, so it's kind of exciting, so I put that picture there. We outfitted a hospital room in the Clinical Sciences and Translational Research Center at UNM with LED-based full-spectrum lighting, as well as time-of-flight sensors and color sensors, with the goal of being able to provide full spectrum variable lighting at the right place and the right time. The goal is to be able to ultimately design lighting strategies beyond simply intensity, so just on-off essentially, or how much on, how much off, but also change the spectrum to help healing and other health benefits. Right now we're looking at folks who are delayed sleep-wake phase disorder with the goal of just doing a validation study showing that we can alter their phase based on what we know about light box studies, which is state-of-the-art aside from this new troffer-based system. And then also working with a neurosurgeon on cerebral spinal fluid dynamics and traumatic brain injury, where we've had access to this fabulous trove of data, highly invasive data from people who have been in very, very bad accidents, car accidents, or had huge strokes, and looking at problems designed to help the physicians treat patients who visibly seem similar but have dramatically different outcomes by identifying relevant trends earlier on in their stay. So I'm going to be focusing primarily here on tools for reliable autonomy. We've been looking at problems in developing formal methods for human-in-the-loop systems for a few years now, with differing levels of fidelity about what assumptions we make about the user. We're interested in systems that have non-trivial interactions, not only between the mode logic that governs the automation, the underlying dynamics of the system, but also potentially multiple human operators in the loop. And so the question of modeling the human is key, because ultimately, if you want to talk about safety or performance of the system, it's going to be based on whatever assumptions you make about the user. So in some cases, we've been following a very generic human model in an effort to say as much as we can, so specifying as little as possible about the human. And these approaches, I think, are going to work best for systems in which the user is fairly homogeneous. They're very well trained. They have a lot of experience. Maybe you're looking at nominal scenarios. So pilots, anesthesiologists who are looking to automate low-level functions, these kinds of things. However, there's many other domains in which having a very, very subject-specific model of the human is much more appropriate. So for instance, assistive devices. This is a very heterogeneous group of people, and every single solution is essentially customized. So subject-specific, generic, there's a whole range of options in between. We've been pursuing some of both, and I'll talk about both of our efforts in that today. So the main goal of the work that I'll be talking about today has been to identify how to design user interfaces that are dynamics-driven, not just simply added on after the fact. In many systems, aircraft in particular, after the control engineers have completely specified the system and designed it, human factors folks come in after the fact, try to reverse engineer the relevant aspects that the operator needs to know, and design an interface accordingly. What we're interested in doing is synthesizing user interfaces that are driven by the underlying dynamics of the system, be they continuous, hybrid, whatever. Computational techniques for reachability of discrete time stochastic hybrid systems with a human in the loop. One of our motivations for this is collaborative navigation in dynamic, uncertain spaces. And characterization of relevant human action and motor control. So again, this kind of speaks to the question of, well, how do we model the human and what's going to be appropriate for these human in the loop systems? There's been a lot of work in this area, dating all the way back to models of the human in the 50s and 60s, where the human was an integrator, fits as MABA list, men are better at, machines are better at. So very dated references, yeah. And more recent work in the human factors domain has focused on describing the limits of human perception and action. We draw in part on some of this literature. We try to codify some of their guidelines for user-centered design into constraints that make sense mathematically, observability constraints, optimality constraints. There's been some work in the formal methods community, primarily from a discrete event systems or finite automaton sort of point of view, model checking to identify mode confusion when you can specify ahead of time discrete event models that represent not only the system's behavior, but also the operator's behavior, the operator's mental model, these kinds of things. And then, of course, in the controls community, there's been work in modeling as well as control of systems that involve a human in loop, decision dynamics, as well as in semi-automated systems. So I'm going to talk first about some of our work in interface design. We view this as an observability problem. This is something that I started with my PhD with Claire. And then also how we have gone from looking simply from characterizing to actually the design. OK, so the human is an observer. So we're presuming a structure in which the user interface lies in between the human operator and the underlying system. It provides a means for the user to provide inputs to the system as well as to receive information about the state of the system. So the output that we're interested in is exactly the user interface. And it is potentially a function not only of the continuous states, but also the discrete states of the automation, as well as any inputs. Now, what goes in the box for the human operator is an open question. As an observer, we're trying to specify as little as possible about the human. We're just looking at the question of whether or not the information that the user interface provides is adequate for the user to complete the desired task. Now, our assumptions about what the user needs is based on human-centered design principles, essentially. And we also want to minimize the information, typically. I've shown a picture of a power operator station at a transmission level center, and also a picture, a very grainy picture of part of an aircraft cockpit display. There's a lot of information, and it's a well-known phenomenon that if you have a human operator with too much information, exposed to too much, they stop looking at it. It becomes essentially useless. On the other hand, if you have too little information, then the display can appear non-deterministic. You press one button, two things happen, and you can't distinguish as to when each of those two things is going to occur. So what's the right information? And can we provide information that is minimal? Now, what we are not doing is focusing at all on how that information is displayed. And obviously, that's a very important part of human automation interaction. We're focusing on that aspect that we can quantify, which is just the information content. The other caveat that I should give here is that we're focusing also on visually displayed information. One of the directions that I'm interested in looking at in the future is how would we do this kind of thing for haptic information, for instance, or acoustic. Right? So human response to these kinds of signals is going to be different than the visual. So everything that we're doing right now is presuming visual information. So we began to look at this idea of if the human is an observer, how are they different from a standard observer? What's unique about the human in terms of how they are going to be able to process information? And what information are they going to have at their disposal in any kind of system? Because some of it we have control over and some of it we may not. So we capture a lot of this in the idea of information availability, which is a term that was approved by some folks in human factors. Basically, there's two ideas. One is that the user needs to be able to reconstruct information about the true state of the system that is relevant for the task that they want to complete. And this needs to happen at every single instant. And the other one is that they need to be able to predict what's going to happen to the system. And we're taking that to mean at the current instant. So instantaneously, we need to know what direction the system is headed in. So reconstruction of the current and the next state based on information that is available to the user. So what information do they actually have? Well, we're going to assume that the user has an accurate mental model for the purposes of this. We're going to assume that they're highly trained. So this is not relevant for the stage in which they're learning a new task. This is presuming that they've already had a chance to practice and they're just putting it into place. So under these kinds of scenarios, we can assume that the user is going to see the current output and be able to process it if they have situational awareness. Okay, so this is how we codify the human factors principle of situational awareness, is that they have access to the current output and they can use it to be able to estimate the current state. The human input is a little bit different. So what we assume is that they know, if you have, for instance, a joystick input, that the human knows the current value of their input. They know what command that they're giving, but that they don't know higher derivatives. Okay, so what this means is that we have some knowledge of the input, but not total knowledge of the input with respect to how the state is going to evolve. The automation input, this depends on the structure that you're assuming for your system. In some cases, you might have access to the information. In some cases, you might not. If, for instance, you're thinking about an aircraft where you provide a reference input and the automation modifies the signal that you provide to the aircraft, then if those modifications are not known ahead of time, and say you trigger envelope protection laws, then this might be a case in which you don't know what the automation is doing. But if it's standard operation, you've interacted with the system before, then we might be able to say that you do know the automation input. So that's going to be situation dependent. Past output and past input, these are the key differences. So user-centered design dictates that it is bad form to have an interface which requires history in order to be able to make a decision about what you need to do at the current instant. So imagine if, in order to operate with your phone, you had to remember what button you pressed 3 buttons ago. That would be really, really poor. So we're going to assume that you do not have access to these things. So the information that you have at your disposal is somewhat limited, and most particularly with respect to the input, whether it's from the automation or from higher derivatives of your own input. So this becomes an unknown input observability problem. So we've looked at a couple instantiations of this. And essentially what we're trying to do is reconstruct the state X. If we're given an output, we have knowledge about the dynamics of the system, which we presume from situational awareness. But we don't know the higher derivatives, and we don't know external disturbances, which is how we're modeling the automation input in this case. In the event that we're doing reference trajectory tracking, we've looked at the cases of supervisory, shared, or manual control. And I'm going to focus in particular on manual control. We're presuming that we have something, some feedback linearization, some sort of controller that allows us to specify what information is presented to the user. And so we chose feedback linearization as an easy way to take care of that. So the idea is that the human provides some sort of reference input. The automation is taking care of the low-level control in order to accomplish that reference input. And it's going to be a signal that is potentially varying over time. Now, the relative degree is going to determine the dimension of the observable states. So that's going to give us what information that the human is going to have. So we can show that the relationship between user observable and user predictable states is such that it is a subset of the observable subspace. And if our task subspace, so the subspace associated with the set of tasks that we want to accomplish. So for example, if you were driving a remote car and you want it to stop at a specific point, or you want it to drive at a certain, according to a certain profile, reference profile, then those task subspaces might involve the position or velocity, right, of your state. So in the event that we have manual control with this reference tracking, and we're using feedback linearization, we don't have to worry about the details so much of computing the user observable subspace and the user predictable subspace, which is part of the reason we're interested in this framework alone. So in order to compute these, we basically are identifying the portion of the state space from which we can reconstruct the state given this lack of information about the higher derivatives of the input and the derivative. So if you apply projection matrices to get rid of the stuff that you don't know, then what you're left with lets you characterize a set of states that you can estimate, and that's your user observable subspace. We then create a transformation into the observable and unobservable to help us figure out how to characterize the user predictable. But when we deal with this feedback linearization case, essentially, the observable dynamics are also user observable. And if we show the automation input, they're also user predictable. So those are the assumptions that I'm going to make from this point onward. The picture I have there is a picture of an Airbus where the pilot has a control stick. This is the pilot on the right-hand side. He's got a little control stick over by the right. The pilot on the left has a control stick on the left. So the take-home message is that the two pilots can't necessarily see what each other is doing. So as far as making assumptions about, in a multiple user case, whether or not, even if the users are collaborating, whether or not they know what they're doing, it depends on the particular setup. In this case, I don't think that you can make an argument that the right pilot knows what the left pilot is doing, even if they're cooperating, right? If you're looking at manual inputs anyways. So we analyze this, and we're able to show that, indeed, that the observable and predictable subspaces were not adequate for the task at hand, which was an altitude following task. Yeah? Yes.
So what is the U? Is that determined by R of t? The control input is fully human controlled, and it's translated to a reference trajectory?
OK. So the human is inputting a reference trajectory, which is fed through. The reference trajectory box is basically making it something that is full state tracking. Okay? So we're taking derivatives of it, basically. The closed loop plant is basically what we get if we apply the reference tracking control law and feedback linearization. And then the state is fed back to the observations, which for that output is fed back to the human.
In that case, U of t is a function of R of t. It's determined by
U of t is a function. OK.
I was just trying to correlate U on the left.
Oh, sorry. Yeah, OK, you're right. I didn't see the, yeah. Yeah, so what I have written on the left was when we were looking at if you had direct access to the low-level control. We then later generalized it to what if you don't have access to the low-level control, you're assuming that the automation takes care of it. But it's the same idea. Yeah, sorry about that. OK, so for the design problem, we basically want to come up with an interface which satisfies these conditions for user observability and user predictability ahead of time. And we're focusing on that manual case, the manual control where, even though it's hands-on, there's a fair amount of automation going on. So we use sensor placement to solve this as an optimization problem. So we come up with a suite of outputs that we represent as a set of sensors. And we're essentially trying to pick the right combination of sensors to meet certain objectives, which codify the user interface constraints and the cardinality constraint. So we look at a variety of scenarios. We're able to talk about nominal and off-nominal operation, as well as noisy and noise-free measurements. Okay, so this is the simplest case when we have no noise associated with our sensors. So we're assuming perfect information. And we're also assuming this is the nominal scenario, nominal operating scenario. So this would be something like everything is normal, you're flying steady and level at 40,000 feet. Right? Off-nominal might be you're trying to do a landing, one engine is out, and envelope protection laws have been activated. Okay, so in the nominal case, the key thing is that the user is going to trust the automation. And we want to take advantage of that fact to delegate as much authority to the automation as possible. In the off-nominal case, we have the opposite, where you don't trust what the automation is doing, and so you want as much information as possible and as much of the information as you can get. So the information objective in this case is simply to minimize the cardinality of the set of sensors that we choose. So each element in the set S is basically a single row vector, which gives us one sensor. Right? So the set of sensors that we could possibly pick is in the power set because we're looking at all possible combinations. So that's the first requirement. It's just feasibility. The second one is availability. So this is the information availability. Essentially, this is the constraint that's going to tell us whether or not we meet the criteria for user observability and user predictability. For this particular case, when we have no noise and nominal, then that's described here. And essentially, the key thing is it's a function of the relative degree, which is now a function of the set of sensors. Okay, so we're looking at what happens to the relative degree if we pick a certain set of sensors. This function turns out to be monotone increasing, which sounds great. But the problem is that we have constraints, so we can't actually take advantage of submodularity. So the availability constraint basically says that the task, if you are trying to track a certain velocity or achieve a certain position, whatever key quantities you describe by that task needs to be incorporated in the set of sensors you're considering. So that's what the information availability is. And then aside from that, basically anything that's observable is going to be available as well. The third one, the trust constraint, is essentially how we codify the nominal conditions. Basically that if we trust the system, we want to give it as much authority as possible, so we actually want to minimize the relative degree. We want it to be as small as possible. So this is the relative degree of S is equal to the smallest value you could possibly take. Now the intersection is denoted in this yellow area, and we don't know ahead of time whether or not that's actually going to be non-empty. So it's possible, if it's non-empty, then it's a fairly straightforward thing to enumerate. We basically just have to order the single cardinality ones, look through those, then the cardinality 2, look through those, that lie in this feasible set. And so we don't actually have to solve a full combinatorial optimization. It turns out that we can bound this polynomially. In the event that that intersection is empty, then there are suboptimal solutions that we can find. And we have algorithms as well that take advantage of, that are greedy. In the case that we have off-nominal operation, things are fairly similar, except that now we want to maximize the relative degree because we don't trust information. We don't trust the automation to do the right thing necessarily. So we want as much information as possible. And in this case, okay, so there's two things. One is that it becomes a set covering problem. The other interesting thing is that we can actually show that the constraint due to trust gives us a subset of the availability. And this is because now we've got gamma max instead of gamma min. So this is, of course, an NP-hard problem. There are suboptimal solutions that we can find more easily. For the problems that we've been looking at, they've been small enough that it hasn't been an issue. But for larger systems, of course, this is going to be more relevant. So basically, the take-home message is that this gives us the set of sensors that are minimal cardinality for maximal observability. Now, when there's noise, essentially the data that the user has access to is unreliable. So we're presuming that the human should be MMSE observer. And so we want to maximize essentially this cost function, which is going to give us the smallest volume uncertainty ellipse. So we're assuming that our ellipse satisfies conditions that allow us to write it down this way. The availability and the trust constraints are not changed. We can do a similar sort of analysis as we did in the non-noisy case, where we first look at the intersection, identify whether or not it's empty, and then apply the appropriate algorithms. These are more complicated. Our main difference here is that our cost is now going to be instead of cardinality, it's going to be the minimization of that uncertainty ellipse. So we want to minimize the uncertainty associated with the observations that we do have. So we applied this to a very small system, a small leader-follower formation of UAVs with the structure shown in the top, where 1 is the leader and 2 and 4 are the tail. We were looking at the leader tracking a waypoint, and so outputs include position and speed of each vehicle. That's our set of sensors that we would consider. For each of the different scenarios, what this returns is different selections of sensors. So for the nominal noise case, it's pretty much what you would expect. If you have this structure and your task is to have the leader go to a certain waypoint, you just need information about the leader. If you trust the automation, then the rest of the system is going to behave in the way that you expect. If you presume that the system is not reliable, not operating as you expect, then you want as much information as possible, so you need information about the position of the tail vehicles in addition to the one that's carrying out your task. In the in the noisy case, you see that there's velocities that are included. It's because essentially we want to minimize the uncertainty, and because that's a lower derivative, we want to basically take that one instead of the position. We don't have to integrate the noise. So we're right now looking at extensions of this to hybrid systems, specifically switched LTI systems with application to a model of the transmission system, which, right now we're just looking at the 118 bus, but we want to do something a little bit more realistic at some point as well. And there may be things that we can do in terms of exploiting matroid form. Okay. So I'm going to talk a little bit about some of our work in collaborative navigation. We've been looking at problems in stochastic reachability and viability, standard formulation, where we're looking for the ability to reach a target set with a certain likelihood while potentially avoiding a set of states that are considered to be bad. There's been a lot of work in this area, and computational tools that have been developed have been primarily based on dynamic programming, although there's been some others that are more efficient more recently. We've been looking at two cases. One is the imperfect information problem. This is work by Kendra Lesser, who graduated a couple years ago. She was able to show, that, as other people have identified as well, that it's a really difficult problem. The belief state is a function in L1, so computationally prohibitive for even small systems. So she came up with two ways of approximating it using point-based value iteration, so basically POM-DP methods. The perfect information problem is huge, but through both the finite state approximations as well as Gaussian mixtures, she was able to show convergence that's dependent on the fidelity of your approximation. And so in the finite state approximation, the more you grid, not just your state space, but your input space and your observation space, the closer you get to the true value function. With the Gaussian mixtures, she uses Gaussian radial basis functions to do everything, including the indicator function. So there's obvious disadvantages, including this Gibbs-like phenomenon that appears. When we specialize to deterministic dynamics with imperfect information, so basically we just have measurement noise but no process noise, we had a little bit better luck. So the belief state in this case is a truncated Gaussian. So we can specify it in terms of the mean, the covariance, as well as the truncated set. And we can identify clearly and cleanly how that truncated set is going to propagate over time. That's what those pictures are showing. If we use this in conjunction with adaptive gridding, then things can be a little bit better. The computational times that are shown here are for a two-dimensional room heating problem. So 2D is obviously something that would have been beyond us with the dynamic programming, but this way we do get results. Which one is better depends on the problem at hand. The pictures that I've shown are also an application to dynamics of anesthesia delivery, which was a three-dimensional problem. We also did some work in using particle filters and chance-constrained optimization for the perfect information problem with application to space vehicle docking and rendezvous. This is work that was in collaboration with folks at AFRL. We were able to do a four-dimensional problem here. The full CWH Closey-Wiltshire Hill equations are actually 6 dimensions. They're decoupled, though, so we were able to look at just the 4 separately. OK, so collaborative navigation. So I've been working with Lydia Tapia, who is in motion planning, to look at the problem of navigation in highly cluttered, dynamic, stochastic environments with hundreds of moving obstacles. So we've been pursuing a couple of different approaches. We started out by simply doing pairwise stochastic reachable sets between the robot and any obstacle, where we had certain classes of obstacles that let us pre-compute these things fairly efficiently. So the obstacles were either straight line or arc with stochastic speed. We used then the stochastic reachable sets to weight motion planning algorithms. And the picture up on the right is a grid-based method. We looked at probabilistic road maps. Here is an artificial potential field method that we're using where the heat map indicates the likelihood of collision. So we lose all guarantees, right? Because we computed the safety pairwise, and the actual environment has multiple obstacles. But we see dramatically improved performance, which was kind of nice. This is a movie showing some of the grid-based methods that we were applying. We're comparing them to standard sort of methods. SR query is stochastic reachable set query. That was the method that we were hypothesizing. So the two different algorithms are shown in the blue and the black. The red obstacles are straight line or arc. And then the goal is to get from the lower left to the upper right corner. So sometimes, Sometimes our algorithm doesn't do as well, but a lot of the time it does, and it significantly outperformed others. So we had more luck when we were looking at artificial potential fields because it allows us to choose the control action more often than with the roadmap-based methods. We were also interested in combining static as well as dynamic obstacles. So she picked some environments that were very complicated from the motion planning side of things and then threw a bunch of obstacles in it. So we've got two other algorithms that we're comparing it with in the bug trap. The red path is the nominal path it wants to follow. And our vehicle is a small red dot that's weaving and bobbing around it. We're assuming perfect information in this case. And we're also assuming that we have perfect knowledge of the statistics of all the other obstacles in the environment. So this is another one, similar sort of story. So the obstacles are also traveling through walls. They're not hitting each other, these kinds of simplifications. Okay, now the collaborative part comes in how this information is conveyed to the user in a way that will help them do this navigation task. So the thought is that we need to compute an automated solution that we would implement irrespective of the human. But how we actually merge that with the human's desired input and what information we convey to the human is an open problem. So we've developed a little game. Let's see, I don't know if it's playing. It is playing. That's going to be released through the Google Store. Busy Bee-Way. So basically, the bee is the robot in the center, and it's not doing anything because in this video, it's just static. But that is what the user would be controlling. The other bees are considered the obstacles in the environment. And so what we're planning to do is come up with a suite of different displays. So we're working with a human-computer interaction person who is providing information about hypotheses about what display of uncertainty is going to be most effective. So there's two open issues. One is how do we best display the uncertainty in a way that's going to be useful to the human, especially given that we want to keep the information from being overwhelming. And then the second thing is how do we appropriately interfere if we need to with their control actions. Now the first stage that we're planning is we're not going to do anything. We're going to let the human decide fully the control action. But we'd like to look at other human automation paradigms as well, not just this, manual, supervisory, shared, the whole 9 yards. And so this is going to be, I think, a good way for us to be able to do this. So we've already got the IRBs, and we're ready to go with our user studies. The undergraduates are coding up the various uncertainty displays, and that'll be the first set of experiments we run. So we've also been looking at forward reachability with uncontrolled reachable sets as a possible alternative to get around some of the computational complexities and the lack of guarantees that we have. Now, forward reachability, is not going to give us the safety guarantee, but it does give us a constraint that we can use to avoid bad regions with a certain likelihood. So we don't know that a solution is necessarily going to exist, but if we do adhere to these restrictions, then we can guarantee that we're going to have collision avoidance with a certain likelihood. So we define our forward stochastic reachable set from a given initial condition in an initial set for a specific instantiation and a specific specific random variable, instantiation of the random variable. The nice thing is that we can actually, because we don't have a control, because we have this nice affine form, we can separate out the calculation of the reach set and the probability measure. And the probability measure can be written as a convolution. So this means we can compute with it. So if the reach set has dynamics that are things that can be handled with existing tools, MPT, the ellipsoidal toolbox, then we can do both of these in fairly short order. And what's more is we can get an exact result for a countable disturbance set. So this is just an example with MPT for, this is an LTI system with a Gaussian distribution, dynamic programming, 259 seconds, 1.2 with MPT. So one of our applications for this is non-adversarial pursuit. So we're looking at the problem of how do we catch a pursuer who is moving in some sort of stochastic fashion, how do we best catch them? So first of all, can we do it from our given initial configuration? And where should we go to maximize the likelihood of catching them? And this is with, I've shown it here with multiple pursuers. We've also looked at the single pursuer as well. Turns out that we can write this as a convex optimization. And for the multiple pursuer case, we simply write the catch probability, the likelihood of getting to the desired state, the desired space, as whoever gets there first, basically. So we basically can solve it for each pursuer separately. So we're assuming we have one stochastic obstacle that's moving in a fashion that is not interacting with us. And then we're simply looking for the region associated with the box. That's our capture set, the little pink box, that lies, so these little pink boxes here, not the big one, but the small one. This is the capture set that we're trying to acquire, that lies with the highest likelihood. So this is showing something over time. They start here, and then they go here. This one's the third one. This is the fourth one. So the reach set is getting bigger and bigger over time, as you would expect. And our uncertainty is also getting bigger and bigger over time. What's shown in the top is the optimal solution if we compute this for stochastic forward reach set for a given horizon. We've discretized time. So if we were to look for the reach tube solution, we can't show convexity. But if we do it to reach set, we do show convexity. So we've done that, discretized time, and we can do this arbitrarily finely, and then simply pick the one that gives us the best result. So in this case, you don't want to let the system go too long, because then the uncertainty associated with its position is too large. So there's an optimal one here that's at the time step 4, and then the blue guy has the highest likelihood of catching the evader at that time. We've also applied this to the problem of dynamic obstacle avoidance. So this is basically the same problem as the videos that I showed earlier. But instead of doing it with motion planning, we're just doing some simple MPC to solve the control problem. So we compute the forward stochastic reach sets for each of the obstacles separately. It turns out that this is, as other people have identified as well, even if you have a convex set for a single obstacle, when you have multiple obstacles, you're not going to get something that's necessarily a union of convex sets. So we do have to do an under approximation. So we identify super level sets of the occupancy function, which tells us where we could potentially hit things, and then under approximate it so that we can avoid online convexification. So basically, what we're doing is enabling some offline computation so that we can do the mixed integer linear program to do navigation online. Again, we're looking for solutions that might be eventually amenable to real-time operation. The other application of the forward reachable set calculation has been with something that we're calling dynamic risk tolerance. Essentially, what we're doing is using some of the existing motion planning methods, but changing our threshold for what we consider to be acceptable likelihood of collision as a function of time. So the problem is that if you insist on a very low likelihood of collision, you're assured to have safety, or with higher probability, but it's very hard to find a feasible path. On the other hand, if you increase it and you allow for very high likelihood of collision, you're going to have a feasible path, much more likely, but you may not survive it long enough to see. So the answer was to do something on the order of a time-varying threshold, and we've arbitrarily chosen a suite, a step function, a linear-looking function, and an exponential climbing function. All of which have the shared characteristics that the likelihood of collision is the threshold for collision is very low initially, and then it grows over time, so that you can still have path feasibility but still enforcing a lack of collision in the immediate vicinity. So the planning is a tree-based method with multiple stages to take into account these different risk tolerances. And then the prediction of obstacle locations, which is key for this, is done via forward stochastic reachable sets. So this graph basically shows that our method has better success rate than comparable methods, including our own previous efforts. OK. So I'm running out of time, so I'll talk very, very briefly about this. We did some work on validation of human-in-the-loop models with some folks at Carnegie Mellon, Katya Sakara's group, and Christian Labier. They're using ACTAR to come up with simple models of how humans would accomplish certain tasks. They deployed a 2-choice game on Amazon Turk. And we've identified a way to validate or invalidate the model based on a comparison between expected performance with ACTAR using forward reachable set analysis and existing data that's been gathered from users on Amazon Turk. So we were able to formulate our expected outcome in terms of a forward reachable set calculation by taking advantage of the fact that we have a mostly deterministic system with occasional events, and the events are with the source of the probability. So those are the only source of uncertainty, rather. So infrequent discrete choice. If we had to do this more often, then computationally it wouldn't work out. But because we don't have to do it very often, we can simply propagate the deterministic dynamics and then just take a look at the sets that result and intersect them appropriately as we evolve the expected outcome. In this case, the outcome was the outcome was the expected area of coverage when you choose either rendezvous or deploy, one of two strategies, based on just the initial configuration. I wanted to talk briefly about some of the work that we're doing in Parkinson's disease. We had a manual tracking task. What we're interested in is characterizing submovements. So there's a couple of things that are really interesting about this. One, that we can characterize submovements. So these are open-loop motor programs that the brain selects between. So the thought is the cerebellum has picked these open-loop motor programs that we've learned over a lifetime, and the basal ganglia is essentially switching between them as necessary to create these seemingly smooth movements. We have a motor tracking task, which, if it's tuned to just the right level of difficulty, appears to be allowing us to see the submovements, which is a really cool thing. The reason that we're interested in this in Parkinson's disease is that there is an interplay between the basal ganglia and the cerebellum that is thought to be interfered with basically by Parkinson's disease. Some of the faulty feedback mechanism is associated with prediction as well as control, closed-loop control. So our hope was to identify interesting points in the manual tracking data, correlate them with concomitantly gathered brain data, in this case EEG, and then see if any of the phenomenon in the connectivity as well as the manual tracking makes sense. So our preliminary results are interesting. So basically we did a hybrid system identification. It turns out that there's only 3 types of submovements, which is a wonderful simplification. Tracking, rest, which is when they're basically taking advantage of the joystick and just letting inertia do its thing, and then correction when they're actively going against the existing trajectory. So they have these jerky movements. So Parkinson's disease, there are thought to be issues with reward. So switching thresholds are also of interest, and this is something that we're looking at now. We've done the identification. We've found significances in when changes with respect to L-DOPA as well as with respect to some non-invasive stimulation that we think might be potentially helpful for mitigating some of the symptoms. And it seems to make sense with what we know about Parkinson's disease and the effect due to medication, L-DOPA in this case, namely that it compensates for cognitive inflexibility. There's more dwell time in the correction and less with rest if we look at the difference with respect to medication. And the root mean square error actually increases from tracking to rest, so from this one particular transition. So now we're trying to look at, now that we know when the modes occur, what do we know about when the transitions are triggered? If instead of assuming we have a switch system, what if we have a system where there are thresholds that trigger the switching? We're trying to recreate what those thresholds are. So we're using classification to identify the hyperplane, and then figuring out how to compare those across subjects is where we're at right now. There's a lot of heterogeneity, and figuring out what the right way is to compare all these different pieces of data is still an open problem. So we're working through that right now. OK, so let me stop there, since I don't want to go over time, and I would be happy to take any questions.